X and Y are members of your language. Right? And what is a language? A set of strings. Okay? So here, you're creating usually a very large set. Let's say the number of strings in your language A, let's say it's finite. Let's say big N. So you have big N different strings in your language A. So what you're doing here is you're concatenating as many times as you want members of A. Now remember, what is a member of a language? So it's an input string, right? So you in A star you would put all combinations of concatenations of strings from A. And it's probably easier to actually give you an example to explain it. Let's say so your alphabet is just the ordinary alphabet, the Roman alphabet. Let's say so that's your alphabet, and then let's say the language has just two. Language A has just two input strings. Okay, good and bad. As strings, right? In other words, G-O-O-D and B-A-D, right? They're the two input strings. And so A star would be all possible concatenations of elements of A. In other words, good and bad. It's only two. We keep it simple. To any number of concatenations, like if you had K, so you could have a concatenation that would have K, total of K of this string or this string. For example, let's do it systematically. Let's say K is 1 here. So you just have one string here. Now, well, if K is 0, K could be 0. K is less or equal to 0. So if K is 0, you don't have any string. Well, that's the empty string. So here, you start with the empty string. Okay? And now let K be 1. So you just have x1 here. And what is x1? Well, it's one of the elements of your language. It's one of your input strings. Now A star is a list of all possible combinations of concatenations, all possibles. Well, if K is 1, we just have one string here, so x1, which could be good or bad. So good, bad, right? Now let's have K as 2. Put K as 2. So now we have two strings concatenated, and each string, whatever it is, it belongs to your language. Okay? So we can have a concatenation of x1, x2. Now x1 is either good or bad, and x2 is also either good or bad. So we're now we'll have four possibilities, 2 by 2, different concatenations of those two strings, x1, x2. And here they are. Well, you have good, good, you could have good, bad, you could have bad, good, you could have bad, bad. Okay? So you've got four combinations, four possible concatenations with two strings concatenated. Okay? And you can see where this is going. All right. Well, now at K3, so we're now concatenating three strings: x1, x2, x3, and x1, x2, x3. They're all members of the language. They're all, in other words, they're all input strings. And so x1 could be good or bad, x2 could be good or bad, and x3 could be good or bad. So we'll now have 2 by 2 by 2, we'll now have 8 possible different concatenations. We could have good, 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 we could have good, good, bad, we could have good, bad, good, we could have good, bad, bad. You just go through the binary numbers, from 0 to 7. Okay? So good, 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 bad, good, bad, good, good, bad, bad, and so on. Right? There'll be 8 of these 3, and then you could have k as 4. So then you'd have 2 to the 4th, 2, 4, 8, 16. You'd have 16 different concatenations, and to the 5 you have 32, and so on. Now, when does it stop? So A star could become huge, right? Exponentially, grows enormous. So now, is A star infinite? There's no limit here on k. I think thinking real time here. I suspect A star is actually an infinite set. Right? I don't think there's any limit on k. Right? Well, I'll leave that as a question. If there is no limit on k, if this can just be a countably infinite number, well, that means that A star is an infinite set, right? Countably infinite. You can actually count off each element, each member of A star. So it's a countably infinite set, but nevertheless infinite. Whereas here there's no limit on k, right? It's just told to be it's a non-negative integer, right? All right. Okay, so I hope that's clear what star means, right? As a regular operation. It's the set of concatenations where each string, each member in the concatenation is an element of your language. And here's an example: A star, right? And I suspect A star is infinite, an infinite set. Okay, so new sort of topic. Now talk about the idea of closure. Very, very important in pure mathematics, very important in computer theory as well. For an operation, for a set to be closed under a certain operation, what does that mean? Well, in general, like if you've done, if you did my finite group theory course, if you followed that, you will know that closure is a critical concept in the theory of groups, finite groups. So if you've done that, the idea of closure will be quite familiar to you. If you're not familiar with the idea of closure, I'll give it to you now. Take some. I'll give it to you in the abstract, in the general form. Take some set and some operation. Now let's call the set. Let's call set S, okay? And the operation is P, whatever it is. Now you take this operation, might be take the square of, multiply by, whatever. So some operation P, you apply that operation on one or more members of your set S, and you'll get a result, okay? So you apply operation P on one or more members of your set S, and you'll get a result. If that result is also a member of your set S, for all cases, all possible cases, that set, by definition, is said to be closed under that operation P. Right? That's the general. Now, if you didn't follow that, well, you rewind. But let's do a concrete case. Maybe it'll become clearer. Things are getting a little dark. I'm going to switch on the light and put on my hat. Just a minute. Okay, I think that's the first time I've done that in real time. I mean, put on my hat. Okay, so let's do a concrete example of closure. Say your set